Good afternoon, everyone. We're so glad that you've joined us for the Tulane Future of Energy Forum. It is my pleasure to introduce our next session, Unlocking the Potential of Fusion in the Energy Landscape. Please silence your cell phones, but keep them handy. We'll have a QR code that you can scan if you'd like to ask questions that the panel will address at the end of the session. And now please join me in giving a warm welcome to our moderator, the Vice President for Public Affairs and Chief Communications Officer for Tulane University, Ian Morrison.
Thank you. Okay, good afternoon. So first, thank you everyone for joining us. Thank you to our panelists for being here from, I was going to say far away, but DC and Boston. This is great. I hope you're all as excited as I am to hear more about fusion. Sneak preview, it's not the stuff of sci-fi anymore. I had an opportunity to have a great prep call with the group, and I'll be honest, I didn't know a lot about fusion myself, and I came away really fascinated. An incredible amount of passion, energy, pun intended, and just incredible promise of this technology is really interesting and inspiring, and I hope you think the same. And then obviously, lots of others are excited too. If you haven't seen it yet, there was a great write-up in the New York Times this morning, also featuring Ben's company, which was really great and worth a read. I definitely read it as a great primer for the conversation today. So we have a great conversation in store. So what I'll do is first I'll introduce each of the panelists, ask them to tell us a little bit about themselves and how they got to be involved in fusion, and then we'll get things going. So Sierra Cato, you're the Principal Energy Policy Practice Group for Lewis-Burke Associates. Tell us a little bit about your journey and how you came to work on this technology.
Yes, thank you, Ian. Hi, everyone. I'm Sierra Cato. I am a principal in the Energy Policy Practice Group at Lewis-Burke Associates in Washington, D.C. We are a government relations and lobbying and consulting firm representing the interest of many fine institutions like Tulane, scientific societies, private companies, including a startup nuclear company as well as a fusion company that's in our portfolio. Basically, we make sure that our institutions have a voice in Washington, that their interests and priorities are being heard with policymakers and decision makers. We help position our institutions to collaborate with the federal government to make sure that they are advancing their scientific, energy, and technological priorities as well. But I got into fusion just from my background in being in energy and Lewis-Burke Associates, and looking forward to kind of helping the industry grow.
Great, thank you, Sierra. Ben, I'll go to you next. Ben Byboth is the Director, Power Business Development and Strategy, Commonwealth Fusion Systems. Also, I'll add a Tulane graduate and former and always New Orleanian. But please tell us a little bit more about your background.
Yeah, sure. So straight out of high school, joined the U.S. Navy, spent 8 years on submarines, working on basically small modular reactors before they were popular. And then I went to commercial nuclear power for about 8 years after I got out of the Navy. I actually worked at the Waterford 3 nuclear plant just down off 310 in Luling, started off in operations and made my way up through engineering, then up to plant management roles. And then I moved over to the utility side of the business where I worked here at Entergy leading innovation. Most recently, I was Director of Grid Modernization for Eversource, a big utility up in the Boston area. And then came over to CFS where we are now working on commercial fusion power. And we'll talk a little bit more about what that landscape looks like in a minute. But we're now just went over 1,000 employees, so we're the largest private fusion company in the world. We're building a demonstration device. I'll show you a few pictures of that later to get you excited about what we're working on. But it's really coming sooner than you think, and I'm looking forward to that part of the conversation.
Thank you, Ben. Andrew, you're next. Andrew Holland is the CEO of the Fusion Industry Association. Tell us a little bit more about your background.
Well, thanks, Ian, and first of all, thank you all for being here and your interest in the next generation of energy. So the Fusion Industry Association is the association representing all of the venture capital-backed startup fusion companies. We have right now 37 companies as members. Anticipate a couple more joining fairly soon. I am based in Washington. We are Washington-based, but our job is to be kind of the collective voice of the fusion industry towards the U.S. government and also to governments around the world. And so we are the representative voice of all of the fusion companies. I came to this, I worked first on Capitol Hill in both the House and the Senate for a number of years, and then worked in public policy and think tanks, and wrote some about everything from energy security and national security into fusion. And so we started the FIA about 3.5 years ago, and have grown pretty quickly since then, along with the industry.
That's great. Thank you. Okay, Andrew, let's stay with you. Can you kind of give us a little bit of a high-level overview to start the 30,000-foot view on fusion?
Yeah, so I think it's really important, and I'm not going to go. My first rule for all of these things is never put equations on a slide. Yeah, I think it's really important when you're talking. Like any science or technology issue, you can go as deep and as technical as you want, but I don't think we need to do that. What you need to know about fusion is that what we're doing is we're taking light elements, hydrogen, helium, boron, those sorts of things, and subjecting them to extreme temperatures or pressures. And at those pressures, the atoms collide and fuse. And in that process of fusion, it's the E equals mc squared equation that you remember from, that's the one equation I'll do. The E equals mc squared equation from Einstein means that a little bit of energy is a little bit of matter turns into a huge amount of energy. And so fusion has this opportunity with very easily accessible fuel to be something that can release a massive amount of energy. The thing also to know about it is that fusion is something that we've been working on for a long time. Scientists, engineers have been working on for a long time. And getting to those extreme temperatures and pressures has been challenging. Doesn't mean that we don't know how to do it. We do fusion every day. This is, like you said at the beginning, this is not a science fiction thing. This is moving from the labs, from science, to the marketplace. And I think actually the private industry is the real signal moment for that here. We've gone from when we started the FIA in the spring of 2021, so not even 4 years, we've gone from about $1.4 billion invested into private industry to over $8 billion invested in that time. That is, if anything, a disruptive change. And is a signal that investors say that this is something that's not only theoretically possible, but is a business that I can make money off of in the time horizon of a usual VC, so 10 to 15 years. And so we've actually asked our member companies, when do you expect to see fusion on the grid? We surveyed them out, and 89% of them said they expect to see fusion electricity on the grid in the 2030s or before. And so last I checked, it's almost the end of 2024. That puts it 10 years away, and companies are on the pathway there. They're on their way to getting there. And the fact that there are 37 companies should also be kind of a signal that there's confidence here, but it's also a market-based way of doing it. Because we are at the bleeding edge of scientific advancement, the market doesn't quite know which one's going to be the right one that's going to get there, which one's going to be the most efficient, which one's going to be able to do it all. So it's a market-based approach that is saying, we're going to try this, we're going to fail, we're going to try something else, we're going to fail, and ultimately the market will choose several different approaches, each of which has a real way to get that huge amount of energy for relatively small input. It's a true game changer.
That's great. Thank you. Ben, what is the CFS approach to this?
Yeah, I appreciate that. And Andrew, thanks for all your support. It's a real industry that's coming together now that's behind this, and CFS is one of those companies. Just a little bit about CFS. CFS was founded in 2018. We were spun out of MIT's Plasma Science and Fusion Center. You can see a little picture of our headquarters here. I've got a few pictures of you to kind of show you how much progress we're making on this goal. CFS started off on the mission to show that we could bring a new class of magnet technology to the fusion landscape. So the type of fusion we do uses really big magnets to contain plasma so we can get those particles to accelerate and ultimately collide and get together. In order to contain these plasmas, we use really strong magnets. A breakthrough in new magnet technology was discovered in 1986 and won the Nobel Prize, and we've been advancing that technology and leading in that space. In September of 21, we demonstrated the ability to make a 20 Tesla magnet. That's a very strong magnet. That's a magnet that can lift an aircraft carrier off the ground if you had a crane strong enough. And then that magnet showed the world that, oh, this existing architecture from these devices that have been built since the 1950s now has the type of breakthrough that can make this really viable. Because when you make really strong magnets, you can make actually commercially viable sized devices. And that's really where our breakthrough comes together, and I'll show you some pictures of that in just a second. And so that's how CFS formed, and now since that magnet, we've raised over $2 billion of that $8 billion. We have the largest Series B raise in Massachusetts state history for a startup company. We're backed by a lot of, almost every name in climate that you can think of. Personally, Bill Gates has invested in the company, Khosla, Koatui, just go down the list. We've got major supporters from like ENI and Equinor. So there's a lot of support with patient capital behind this project who realizes the opportunity. We're talking about the energy transition itself, largest market transition ever. There's over 8,700 power plants in the world today. So that's what we're doing. And let me just kind of click through a few of the pictures and to show you the pace at which we're moving. We're building a demonstration device we call Spark in Devens, Massachusetts. It will integrate the new magnet technology. We started that project in 2021 in June. Here's what the campus looks like today, just 3 years later. And so we're moving very, very quickly. In the foreground is our manufacturing facility where we're building these new class of magnets. In the background's our demonstration device. That device, again, we call Spark. It's going to make about 160 megawatts of heat energy. It won't be a power plant, but it will show the world that you can continuously make energy from a machine, literally grams of matter making ultimately gigawatts of electricity. There's another front view of the device. If you're looking from the front, these are the big cryogenic plants. They're going to cool down the helium that we use to cool our magnets. This is looking up from the bottom underneath where the structure will go. The smallest pipe you see there is actually the fuel header on the right. That little pipe is about as big as your finger. You carry about a few grams of fuel that will make that 160 megawatts of power. We have a lot of power electronics associated, so we're making a lot of ground on capacitors. There's a look at the vacuum vessel, and inside this vacuum vessel, you'll have a plasma that will be about 150 million degrees on the inside of it. And on the outside of it, magnets that are cooled to about 40 Kelvin. That'll be the largest temperature gradient in the universe, separated by less than a meter. Here's a look inside of the facility where that's going to be assembled. That's inside the tokamak hall. You can actually see an image of our device on the right. That's about 9 meters tall. And that device is the one we call Spark. And I mentioned the magnet manufacturing facility. So we moved into that facility in 2022. And you can see what that looked like. This is what it looks like today. So a buzzing environment, making in full production mode, making magnets, stacks and stacks of magnets that will go into our fusion device. And you can see the scale of the hardware that we're taking that capital investment and turning that into new products that will deliver. And this is really the kind of the company slide on a slide. The MIT project, the Alcator project, the first one was built in 1969. They just retired the last one. It set records in plasma temperature and pressure. Our CFO, our CSO, and almost every C-something-O has a PhD plasma physics degree from MIT. We showed the world a magnet in 21. Now we're putting that together in Spark, which is under construction today. That'll turn on in 2026 and have its first plasmas in there. And then we're going to start construction on our commercial project, which we're in the process of siting right now. That'll turn on in the early 2030s and put about 400 megawatts of electricity onto the grid. So that's how close we are. And I think that's maybe some helpful context.
Very cool.
Thank you, Ben. Fascinating. Sierra, turning to you. Okay, let's go back kind of a little higher level. Tell me a little bit about, fusion is often touted as kind of a cleaner, safer form of energy, particularly in relation to nuclear. Tell us a little bit about the risk-benefit there.
Yeah, so fusion is definitely one of the most environmentally safe forms of energy. I get my stats from the International Atomic Energy Agency, and they kind of dive in and saying that, because fusion doesn't emit any carbon dioxide into the air or any other, if you will, harmful type of atmospheric gases, it is, one of the most safe and cleaner forms of energy, and it doesn't, this means it doesn't contribute to greenhouse gas emissions. And as you've heard my colleagues up here say, all the high extreme temperatures that it will take for a fusion reaction, even with those high temperatures and extreme conditions and extreme environments, there's still no potential for a runaway chain reaction or a nuclear meltdown. When you think about terms of waste, the good thing about fusion as well is there's no highly radioactive waste. There's no, it's just a low-level waste, but it doesn't pose any serious danger to the environment. And because the reaction can stop in any minute, it can be halted in any second. Fusion is just regarded as more inherently safe. So I'll let Ben or Andrew, if you all have anything else to add on the safety and environmental benefits.
Yeah. The clear thing on safety to know is that sometimes people say, "Oh, a sun, that sounds really dangerous to have down the street," but but the thing to remember is that it actually, it's this extreme temperature, but it's in a tokamak, it's very low volume. So it's like the difference, think of it this way. It's the difference between if you put a piece of aluminum foil in your oven at 350 degrees or a cast iron pan in your oven at 350 degrees. You can reach in and pull that aluminum foil out with your hand, but I wouldn't do that with the cast iron pan. So the amount of energy in the vacuum vessel at any one time is not an extreme amount. And because of the inherent safety nature of fusion, it is, if anything goes wrong, it's like the best failure mode you could ask for. It automatically turns off. The nature of fusion is that it's hard to start and easy to stop. And that makes it inherently safe.
Yeah, I'd say our chief science officer says it really well, that we build the device to protect the plasma from the environment. Because it's really hard to get the conditions to recreate what happens on the stars in a bottle, and not so much to protect the environment from what happens inside the machine.
Yeah.
And I think when you think about safety, this has been recognized by the regulatory treatment.
Yep.
And what the NRC has decided about the regulatory treatment of fusion is that it will be wholly differentiated from the way that fission's regulated.
Yep.
And then maybe you could touch a little bit more on that, Andrew, from your perspective.
I've spent a lot of time on this. We've worked very closely with the NRC because it was not obvious how fusion would be regulated. And this was really important to investors, to businesses, to have that regulatory certainty. And so we made the case that fusion is so inherently different from nuclear fission that it has to be regulated separately. And so the way it is going to be regulated in this country, in the UK, and increasingly being taken up around the world is like a medical isotope facility, even like an X-ray facility, something at an isotope facility at hospitals. These sorts of things are regulated under what's called the Byproduct Materials Code. But basically it's like you regulate the materials that become this. You don't regulate the whole system itself, because the whole system itself is just not a danger to anyone.
Yeah, I think that the perspective on why that matters so much from a commercial is really important, because if you think about licensing a new SMR technology, you're looking at 10 years and $1 billion to get that license for that design done. Whereas we just got our license for the Spark device that I was showing you pictures of, and that filing fit into a manila folder that we worked with the state of Massachusetts on. The NRC actually subjugates responsibility down to the state level. And so when you're thinking about building a commercial project, and for the finance people out there, if you're looking at 10 years before revenue, the time value of money is going to depreciate that revenue substantially. And it makes the IRRs for some of those big projects very difficult. Whereas on commercial fusion, you have more certainty, so you borrow at a lower risk premium eventually, and that time to revenue is much smaller. So it's a huge difference on looking at these big capital investments and what the risk is.
Great. Let's just change gears a little bit here. Let's talk about the policy landscape. Sierra, I'm going to look to you here. How is federal policy shaping the industry's development at this stage?
Yeah, I'm sure we're all happy to say that the federal policy landscape is shaping out very well. Fusion energy has had a lot of bipartisan support in Congress. As you all know, we've just had a recent election, and President Trump will take office in January, and then we'll have Republicans in control of the House and both the Senate. Well, in FY 2021 and 2021, the first Trump administration, he invested a lot of dollars into fusion energy technologies and also in global efforts as well with an experiment in France. So shifting back to the Congress side, we've also know that Speaker Johnson is extremely supportive of robust research and development efforts. One of the top priorities in the lame duck and kind of next year will be the Energy Policy Act of 2025. So this is comprehensive legislation that covers all areas of energy. The last Energy Act was in 2020, and it also included information and a provision for research and development of fusion technologies. We've seen some of that, as well as more coordination within some of the ARPA-E, Office of Science, and some of the other offices within DOE. I guess what we're looking forward to see more of is, driving the commercialization efforts of fusion once some of the technological challenges, have been solved on the engineering side, and to help drive commercialization. I think we're kind of discussing more of it would be nice. There's a Fusion Energy Sciences office within the Department of Energy, but it would also be great to see an applied energy office, kind of like the nuclear energy office and some of the other offices within DOE, as well as more investments in the technology transition. So in last year, or earlier this year, I believe, DOE set up an independent nonprofit called the Foundation for Energy Security and Innovation. And it's a nonprofit. It's supposed to help drive technology transfer, commercialization, and we're probably hoping to see that continues to go well and make sure that fusion priorities are in there. Another pivotal piece of legislation that covers the fusion industry, and I think Andrew's kind of mentioned on the regulatory side as well, is the Advance Act. So that's what had the regulatory framework in there for the fusion machines, and to make sure there's regulatory certainty and to kind of make sure fusion is separated from other industries that have longer permit and processes, license and processes, and things like that. So the policy landscape is really good. Make sure that you're communicating with the Nuclear Regulatory Commission if you have ideas on any of regulatory framework, as well as weighing into the Energy Policy Act of 2025 to make sure fusion is supported and the right programs are authorized.
Yep.
Did you have something you wanted to add, Andrew?
Just very quickly, I think it's really important to note that the way that the United States is commercializing fusion is private sector led. That this is something that businesses are leading. Businesses are going to be the ones that build the pilot plants that show that this works. And so it's public-private partnerships that are going to be the way that fusion is delivered in the United States. It's not obvious that that's the way. Every other country is thinking of it more as a government project. But of course, I think the United States, leaning heavily on its long history of innovation and private sector led, is going in this direction. And so there's a program called the Milestone-Based Public-Private Partnership, in which they selected 8 companies. Commonwealth was one of them, and then a whole range of others in multiple technology sets. And this is going to be the way that the U.S. delivers pilot plants. It'll be private sector pilot plants, and I just think that's the way to actually do technology development.
And this can be you or Sierra. How do you kind of make that regulatory glide path smoother as you go forward?
Yeah, you just get it done as much as you can before you get there. I think it's really important. We think of it this way: in fusion, you have one huge hurdle, and that's science. You have to prove the science, and once you get over that, it should be a really straight, flat path. You don't want speed bumps in the way. So part of my job as the association, is to go get rid of those speed bumps while the industry works on getting over that big hurdle. In other industries, there is, we mentioned SMRs. That regulatory hurdle is much bigger because of the inherent difference between nuclear fission and fusion energy. And so that's why, we think that, so long as we can get over that big scientific hurdle, we should be able to move and deploy at speed and at scale pretty quickly after we get there.
Thank you. Ben, kind of going back high level again, this is potentially game-changing technology that could have global impacts. How does that play out in terms of geopolitics, energy producing, energy consuming nations?
Yeah, absolutely. I think one of our investors is Temasek, which is the sovereign wealth fund of Singapore. And if you think about fusion as something for Singapore, it's something that really the fuel you need is filtered seawater. It's deuterium. It's 1 in every 500 molecules of water is deuterium. You can filter that from the seawater and use that to make fusion. That means you could have non-blockadable energy. Like all the fuel you need to run a fusion power plant can be delivered on site with the asset. To run one of our devices, one of our commercial projects, it will take 1 welding canister of fuel to run it for an entire year and make over 3 terawatt hours of electricity. And so this is one, from a security standpoint, it's moving to a machine, a device that can create energy. It's not about natural resources. It becomes really about human resources. Can you unlock the creativity to continue to advance the science and the materials that need to continue to bring down the cost to make it all the way to the point of commercial mass acceptance? That is really an engineering challenge now. So this idea that you now are in a place where you're thinking about building machines that make energy. And that's a whole transformation when we think about how geopolitics have been dominated by who has the land, who has the special rocks. That can all change and be liberated by fusion.
Yeah.
Andrew, do you want to add anything to that from your perspective?
Just to say that this is the reason I got into it. Before coming into the association, I worked at and ultimately ran a small national security think tank, and it is this reason, this fundamental change in geopolitics. But we also shouldn't think that the rest of the world doesn't know that either. Of course, the Chinese are now making big investments into fusion because they know that it has this huge geopolitical impact as well. So we expect to see a race getting going here in the global geopolitics to see who gets there first, and because there is a real first mover advantage, and it's time for us to make those investments.
Yeah, we see China is obviously the largest direct competitor when we think about CFS, who's our competition. We see China being right there, looking to duplicate our technology as fast as they can. But there's other countries as well, Korea, Japan, Germany, have all made substantial capital investments into their own enterprises and some of these other companies that are coming together. And so we see a lot of support forming internationally. The UKAEA, the United Kingdom Atomic Energy Association, that group actually was in the forefront of regulations and was something we templated off of in the United States. And that really was, they're building a massive state program. And so there's a lot of excitement globally about fusion. And it's a real race to see who's going to deliver that first.
That's right.
And Ben, I'll stick with you for a minute. In terms of that race, from the industry perspective, what are those milestones that are coming up towards commercial viability that you feel like need to be reached?
Yeah, a good thing about fusion is there's real empirical data that you can pull from these machines. And at CFS, we've been very committed to peer review publications of our progress, of our designs, of our thinking. And we think it's a really important part of the industry's growth and maturity that there's an opportunity for the scientific community to see what we're doing and to follow us along. And even, we have a dedicated group called Open Innovation in our group to work with the universities to try to bring them to the table. Mm-hmm. And so all of that comes together in bringing the package together. And I think when we think about those major milestones, we really need to be able to first be able to make a plasma. You got to get that plasma really hot in the fusion conditions, and then you have to get more energy out of the machine than came in. Otherwise, it's a science experiment. It's not a power plant. But it doesn't stop there. And CFS's mission isn't to show the world that we can make fusion happen one time. It's to build a commercial scale industry that can have a significant impact on climate change. And for CFS, that means being able to reach a place where we can be at somewhere around 1,000 power plants a year someday, being able to produce these things. And so that means that you have to understand the economics. You have to bring something to market that is actually very competitive. So fusion as a science is great, but if we can't apply that technology to satisfy our demands of growing energy and get access to energy, then what are we doing? So it's really, really important that we look beyond just solving the technology problems, and the milestones must include affordable, reliable power down the stream.
Thank you. In terms of public perception and support, and we touched on this a little bit before, but Andrew, I'll start with you in this here. I'd like to hear from you too. What are those public perception challenges at this stage?
So I had a recent conversation with a certain member of Congress from Texas, and I won't name his name, and he said, "Son, all we know about fusion up here is confusion." And he actually said it like that too. And so the truth is that any new technology that comes out, anything new is going to face a real different pressure from the public. They want to know what's going on. They want to know if it's dangerous. They want to know what the impact is going to be. There has been some polling on this, and in general, if you poll it out, overall, if they know about it, they're supportive of it. It's just a bare majority of American voters, though, have heard of it. And that's changed, though, a lot in the last 2 years. Since the big breakthrough at the National Ignition Facility in Lawrence Livermore Lab in California in 2022, that showed for the first time ever that fusion can be done in a controlled way on Earth. So when that happened, it did uptick a lot of the interest, and I can see it in Google searches that come to our website and everything like that. So there's a lot more interest now. People are generally positive of it. They have lots of questions. But framing is also really important too. And that's why, I'm going to tell you a secret here, that's why we say fusion energy and not nuclear fusion. And even though obviously it's a nuclear process, it's completely different. It is in fact the exact opposite of nuclear fission. So the public perception, though, is if you say it's nuclear fusion, the next question then is always bomb, meltdown, danger, radiation. This bears out in polling. If you say fusion energy, the next question then is technology, science, breakthroughs, all these other things. So it's just the framing of this is really important. The truth is, as we mentioned about safety, it is safe. But you have to make sure that you have the right framing, and many companies, CFS included, have done the work of doing the community outreach and engagement in places where they're going to do the work to tell the truth. You don't have to cover it up. This is not, but you have to frame it right, and then you have to go out and talk about why it's important. So we think it'll get there.
Thank you. And Sierra, how does that play out in your work in terms of bridging the divide between the public and policymakers and industry and telling that story?
Yeah, continuing to raise awareness. Like Andrew said, the communication is really important. Some people say, fusion's always going to remain a frontier of science and we're not going to see it in our lifetime, but that is absolutely incorrect. There's a fusion energy caucus on the Hill. We'll see more activity, more policy being coming down the pipeline from fusion. And we're seeing real investments too. We were just kind of talking about that earlier, just like private investments. We're seeing large amount of fundings. It just shows the confidence in fusion, and that's what's going to resonate in this funding environment, in this policy environment.
Absolutely. Thank you. Okay, we're going to turn over to some questions. Just a reminder, you can send in questions using the QR code. And we'll start there.
We have so many great questions. Unfortunately, we'll only have time to get to a few. We've had a few questions about fusion versus solar or wind. Would you place fusion over solar or wind as the alternative energy of a clean energy future? And do we expect that nuclear energy and fusion will potentially replace renewables like wind and solar completely in the future?
I can probably take that one. So I think fundamentally what you really want to achieve as a society is the most affordable energy transition possible. And what that really looks like is a balance between having the low-cost renewables reaching a point of saturation where that there's not a diminishing return of their population. And so in some places we've already started to see a diminishing return, like in California or Germany, where you're seeing prices increase in part. What you really want to do is pair that with firm, clean power to make that energy transition affordable. The Zero Labs group up at Princeton did some really good studies looking at if you could have firm power, your transition from 50 to 0% carbon could be up to 62% cheaper with that mix. So it's not really an either or. It's an integration of the two together such that you can have affordable power that can either serve as a base load or ramp up and down. Fusion can respond like a gas plant does, and it can replace gas on the system eventually. And that's the real optimal point, is that you can take advantage of the benefits of both resources, or all three resources, as best you can.
Next question, if fusion is seeking a distinct regulatory regime, what role can we expect the Nuclear Regulatory Commission to play? Will NRC officials be on site like at fission plants?
No. It's a good question, and like how this is going to work day to day is that federal NRC officials will not need to do the day-to-day regulation of a fusion power plant. Instead, in the United States, it will be done by the states. So that means that states are going to have to, that want to host fusion power plants, are going to have to make some investments to be able to do the regulations. But it will look like many universities host particle accelerators or experimental sort of particle facilities. There's radioisotope labs at hospitals. None of these have all the time, always there, regulators like at a nuclear power plant. But they can always have inspections come through, and so it's the states that will have to be able to do that. The states are ramping up their work and education to do this through what's called the Organization of Agreement States and everything. So it will not be the same way of doing it like the NRC does it. And we should also note that that's only on the radiological side. The other regulatory agencies, whether it's EPA or FERC or the OSHA, will regulate how to keep your plant employees safe and stuff. So it's not like we're looking for some sort of get out of jail free card here. It's appropriate regulation to the risk.
We have a question. While fusion doesn't directly create harmful waste, I can imagine it has a high demand for water and other natural resources, especially for the cooling systems. How does its input consumption level contrast the goal of reduced environmental impact?
Yeah, we think water is very important, and so you can use what's called a dry cooling tower structure and forced air draft cooling towers that can dramatically reduce the amount of water used to almost nothing, other than some moderate makeup and potable water for the staff. And so that's the path we're moving down on our initial designs, is that we see water will just be just as important. If you look at places like Utah right now, you can't build new power plants. You can't even build new houses because you can't build enough water systems. So we need to be able to think and be mindful of a more arid climate, especially in the period of climate change. We think about that. We look at sites. We look at floodplains. Things have to be accounted for this transition and the delayed transition and what that impact means for climate. And so we're being mindful from that, from the design on water and resources all the way through.
Yes.
If fusion plants like the one manufactured by CFS end up in the grid, would companies still be incentivized to develop SMRs?
It's a good question. I personally think, and there's other people that think that you may see electrons from fusion plants before you see an SMR receive a license to operate in the United States. And so we'll see. I think, as a former fission person, I'm a big fan of the technology. I think it can be operated safely. We'll see where the capital investment goes. I think both resources are very capital intensive, and that'll be an interesting challenge to see how the access to capital will play out.
Look, ARPA-E, the Advanced Research Project Agency Energy, within DOE, kind of the investment arm of DOE, has done a study of what to invest in, and the results were everything. The need for the energy transition is so great that everything, it is all hands on deck, whether it's SMRs, hydrogen, CCS, solar, wind, all these sorts of things. And so in the next 10, 20, 30 years, it's going to be throw as much of that onto the grid. And then I do think there will be a competitive marketplace that starts to happen, and it will be, kind of Highlander, one to rule them all, right? I think fusion, of course, I've placed the bet on that. Fusion is the one that I think will ultimately win. But, in the meantime, the need for zero carbon load following generation, firm generation, is so vast that I think we'll see everything on there.
And that's what policymakers refer to as the all-of-the-above energy strategy. I think Secretary Brouette spoke about that yesterday. So, yes, all energy sources on the grid.
Yeah.
Yep.
Considering the scarcity of helium-3 on Earth and the challenges associated with lunar mining, what strategies are being employed to source or substitute helium-3 for fusion research and potential energy production?
This is a great question. So whoever did this has some nuclear background. So there are multiple different fuel cycles that different companies are doing. The one that CFS is doing is a deuterium-tritium fuel cycle, which are two isotopes of hydrogen. That's generally the one that has the most scientific understanding and way forward. And the product of that is helium-4. Now, there's a different one that's helium-3, an isotope of helium that is not widely found on Earth, but it is on the moon. And so we actually have an affiliate member of the FIA that is called Extraterrestrial Mining Company. And they plan to go up and, mine the moon and bring it back. But the truth is that is not on the critical path for the companies that use helium-3 as a way of generating their power. Those that are using helium-3 is you will be able to breed helium-3 from a deuterium-deuterium reaction, a DD reaction. The outputs of that, which you can do to generate power, or you can do it just to generate this fuel. The outputs of a DD reaction are tritium, which you need for the other type of fuel, and helium-3. So they intend to breed their own fuel on site in a breeder plant that then goes into this. So it's a good question, but it fundamentally mistakes the idea that fusion is like another energy source that has to have some sort of resources you have to pull from the ground. And that's the fundamental difference here, is that fusion will be something that can be almost entirely manufactured. And that really does change the equation entirely.
Absolutely. Okay, well, we're getting to time here. So a big thanks to Andrew, Ben, Sierra on behalf of Tulane University, and thank you to all of you.
Thank you all.
And that concludes the session. Thank you so much.